NIOF book, chapter 16. We're taking a look at graphs. This is still coming off that idea of a tree, binary tree. Some of them were search trees, or a digraph. Okay, and that's one, the die is going to be short for directed. So the first one you see here is a directed graph. Um, let's take a look at the whole first. Down here is a directed graph. And you notice this isn't built like a binary tree or even a 2, 3, 4 tree or an M tree where it has, you know, more than one thing stored in a node, may have multiple. In fact, this guy could have as many as 6 links, 6 pointers to go to anywhere, including itself. So there's a potential 6 pointers. Okay. We're going to have a node with one item, a number, a name, something like that. And then it can be connected to one of the others. So I'm thinking this node is going to be built with one data item and 6 pointers. Somehow tracking those 6 pointers. Is it true or is it false? How would we do something like that? And we're going to look at a couple of things in a minute to talk about that. All right, so it differs from a tree in that, well, yeah, there's another thing. There's no root. I don't know where to start. Might be the closest one. A lot of times this gets likened to airlines. These are cities, and we're going to look at something later called a shortest path. But these could be cities, and 6 flies to 2 and it flies to 3. 4 flies to 2 and to 3. And how could we track all of that? All right, so this is called a digraph. Has a finite set of elements called vertices or nodes together with a finite. So again, we don't know how many. We may build a new airport. We may stop flying from one airport to another. So we have these vertices or nodes like 1, 2, and then we have these directed arcs or edges. So the common terms are going to be a vertice and an edge. You usually will hear those the most. And if you want to get into math and discover something and be able to put your name on it, graphing is a crazy thing that there's a lot of unknown that goes with it. I had a grad course one time at Millersville, and it's like, well, it's been proven, things have been proven for this and this and this, but there's no formulas or way to prove things beyond a certain point. And it's kind of an interesting course, but that was, well, 30 years ago. Okay, so now you got the whole. This is a digraph. We have vertices and we have edges. Okay, and as I said a moment ago, they're going to be looking for ways to do the shortest route. Like this is exploded. If you think nowadays in terms of UPS and those types of delivery things, like did you know the route created for a UPS driver eliminates as many left turns as possible? Anybody know why? Because you'd have to cross over traffic and you'd have to actually wait for both lanes to be clear. They try to eliminate as many left turns as possible. Some may have weighted paths. Okay, these edges may be weighted. This is flying to New York City. This is flying to Scranton, Pennsylvania. One of these flights is going to be cheaper than the other because of maybe demand or something like that. We can insert nodes, right? I can throw in 6 and there's 7 and it just sits there. Add edges later. It depends on what we're doing. So going back to that construct, insert, delete, the insert and delete are going to have to work with 2 different things, the nodes and the vertices. Okay. Again, lots of stuff we could write as far as functions that we might use. Again, construct it. Is the whole thing empty? Be interesting to see how you would check that. Can you close down an airport? Get rid of it. Insert a node, insert an edge. delete, no, delete, search and traverse. And again, the traversing the shortest route, we're going to take a look at in a little bit. Okay, so let's see what we got. Um, the first thing we're going to talk about is, let me get a clean piece of paper, something called an adjacency matrix. And let me readjust my camera. An adjacency matrix. Okay. And this is going to be a way to represent representation, a way to represent what we've just been talking about. That is a directed graph. Okay. So let's see, I'm going to create a directed graph. Let's just go around the horn. A, B, C, D, and E. And this would be 1, 2, 3, 4, 5. Naturally, if I said do something, you'd want to start at A. Not always. A goes to B. A goes to C. A goes to E. D goes to itself. C goes to D. B goes to C. C goes to B. It's pretty popular. It's a direct graph. Not sure what we'd use it for, but we're going to look at this adjacency matrix. We're going to represent it as a matrix. We're going to represent it with a 2D array. We're going to use ones and zeros. For example, I mean, I could say A, B, C, D, and E. Across the top, A, B, C, D, and E. Now, if it goes there, it's a 1. If it doesn't, it's a 0. Does A go to 0 to A? Nope, that's a 0. A does go to B. A goes to C. It does not go to D, and it goes to E. Filling the rest out, B only goes to C. So this is a 0, this is a 0, this is a 0, and this is a 0. C goes to B, and C goes to D, which makes these zeros. B only goes to itself. E goes nowhere. Right? So now if I looked at this graph and I said, I want to go from B to C, that's telling me there is one way to get there. I can actually get there. Now, this is a path of length 1. What if I said, I'm at A and I want to get to D? Can I get there? Well, yeah, but it's going to take me, for example, 2 flights to get there. I have to fly to C and then to D. And again, keeping this like an airport is a good way to help remember. Okay, so now we're going back to a math class you may have had. I'm going to take this matrix and rewrite it 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, and all zeros. And I'm going to write it beside itself. And hopefully, some of you will remember how to multiply matrices. because if you can multiply this, we're going to get a result that's kind of cool. Now, how do I multiply matrices? Well, over in my solution, this is row one, this is column one. Row one, column one. So over here, I'm going to take row one, each of the individual elements by column one. And I'm going to multiply them. So I'm going to go 0 times 0 plus. Now I go to the second item, 1 times 0 plus. The third times the third, 1 times 0 plus the fourth times the fourth, 0 times 0, and the fifth times the fifth, 1 times 0. And as you can see, if I add all these up, I end up with a 0. Well, if I take row 1 times row 1 times column 2, that's going to be this next number. And then times column 3, column 4, column 5. 0 times 1 is 0. 1 times 1 is 1. 1 times 0 is 0. 0 times 0 is 0. And 1 times 0. Right? I'm doing column 2 this time with row 1. And I think I actually had a 1 in there, didn't I? So this answers 1. So this was a representation of a length of 1 when I travel. And when I multiply it by another length of 1, I end up getting a length of 2. That means if I start at airport 1, which is A, and I want to go to airport 2, which is B, there's one way to get it with two paths. If I go from A to C, I can get to B. Now, this number can be 2, it can be 3, it can be all kind of different numbers. That would then tell me there's multiple ways to get starting at A to whatever airport I'm trying to get to. Try row 1 times column 3 and see what you get. 0 times 1 plus 1 times 1 plus 1 times 0, 0 times 0, and 1 times 0. There's one way. There's one way to get from A to C by, oh, there we go, A to B to C. And I think if you keep filling this out, this is a 1, this is a 0. I think the next row might look like 0, 1, 0, 1, 0. And we're not going to go through and fill them all out, but let's take a moment or two and practice those, see if you're getting the right answers. I'm going to pause the recording. So we just did number 5. We created a graph. Again, it looks like this. A goes to B, B goes to B. We're now looking at this. 123 goes to 45. 123 goes to 999. Sorry about that. I paused the recording. I think I missed a little bit in the middle there, but should have been fairly easy. Okay, questions on any of that? Directed graphs, digraphs. All right, so we're going to take a look at a digraph. Oh boy. And do I need clean paper? Nah, we can get by here. So we're going to take a look at this graph. All right, A is here, B, C, D, and E. F, G, H, and I. Okay, A goes to B. Let's see, A goes to D. A goes to E. B goes to F. C goes to D. D goes to C. C goes to B. This is actually in the NIOF book. That's pretty good. I'll let you catch up. Okay. All right. So you know all of our things include inserting nodes, inserting edges, deleting them, and on and on and on. And usually we come down to the last thing is we say traverse. Well, if I said traverse through this, you'd be going, I have no idea what you're talking about. And where do I start? Should be a question. Where do I start? You can start at G and traverse as much as you can somehow. Well, we're going to take a look at two different ways to traverse through this. Okay. The first traversal is called depth first. It's called depth first. Now, we're going to take a look at an example. If I did a depth first using a binary tree, and then we'll use the concept to traverse this depth first. Okay, so I'm going to look at a binary tree. A, B, C, D. Well, it's not a binary tree anymore. E, F, H, G. A, B, C, D, E, F, G, H. You notice we don't have arrows on this. This is more of a, I don't know what, I guess some kind of graph. Okay, when I think of depth first, I think of a depth charge, right? The boat's floating along, and all of a sudden it thinks there's a submarine, so it starts dropping and goes down and blows up. So we're going to go a depth first, and we're going to start and go as far as I can. We go from A to B to E, and now I backtrack. I go to B. Can I go farther from there? From B to F to H. Backtracking, but all the way back to A. I go to C. Backtrack to A. D and G. Tree, this would be my depth first search. I go as far as I can and backtrack. Go as far as I can and backtrack. But we're going to take a look at this graph over here, this directed graph, and I'm going to say, okay, let's do a depth first search. Where do you want to start? Did I hear I? Sure. Let's start at I. I goes to H, and that's it. Done. Done. Not a very good starting point. Could be the starting point, though. What's the most natural starting point?
A.
Yeah, you want to start at A. So let's try it starting at A, and I'm going to go depth. I'm going to go A to B to F. I have choices here. Let's go to I. Let's go to H. I'm at my end. I went A, B, F, I, H. I'm stopped. So I go back to I. Can I go anywhere down from I? Nope. Then I backtrack to F. So it stopped at H. I'm backtracking to I. I backtrack to F. Hey, F can go to G. V goes to C. C goes to B. Don't care. We already have that. It goes to D. We don't have that. Now that I'm at D, it goes to H. We already have that. So now I'm backtracking back up to C and all the way to B. Now I come here to E. I already have H. I already have D. So I'm done. I go as far as I can and backtrack. Go as far as I can and then backtrack. You want to try another letter while we're here? Sure. Okay, which letter do you want to pick? About C. If I'm doing a depth first search, where all will I get if I start at C? And again, yours is going to be possibly different than mine. I go to C, I'm just going to go up. I'm going to go B, keep going to F, keep going to G. That goes back to C. So now I backtrack. I can hit I can hit H. Now I backtrack all the way back. Nothing new, nothing new. I'm all the way back to C. C can go to D. D can go to H, already there. D can go back to C. I think I'm done. I don't get to A, and I don't get to E. Again, if I started C, you could have gone to D first, could have gone to B first, but you just keep going and ride that out. We good? Oh, dee dee dee. We're not going to take a look at that same original one I had that was just a search tree. Right, again, this is just a search tree. It's not necessary, it's not binary because A goes three different places. And this time I'm going to look at something called breadth first. Breadth first search, traversal, whatever it is you want to do. Okay. So breadth says I'm going to start at A. From A, where all does A go? A goes to B, A goes to C, and A goes to D. I'm done with A. Now I'm going to take a look at B. Where does B go? B goes to E, B goes to F. I'm done with B. Where does C go? Nowhere. Where does D go? D goes to G. E is done. F goes to H. G goes nowhere. H goes nowhere. So instead of going down, we're going wide. Okay. So I'm going to draw that tree we had a minute ago. It was A, B, C, D, E, F, G, H, and I. A went to B, A went to F went to I went to H. A went to D, A went to E. Shooby-dooby-doo. Pick a letter.
A?
Where might you want to start? This is the easy part.
Wouldn't you want to start at A?
You can start anywhere, remember? Whatever one you live closest to. We're used to going alphabetical, so let's try A. See where all we can get. A goes to B, A goes to D, A goes to E. I'm done that. Now I check B. B goes to F. That's it. D. D goes to C. And that's it. E goes to H. If I go to F, F goes to I. And that's it. C goes to D, which we already have, and B, which we already have. H goes to nobody, and I goes to nobody. Do you notice when I did this, A went to B, D, and E. A went to these three. That was actually like a path of length one. Where all did B go? B went to F. B went to C. And where did E go? No, no. So these were like a distance of 2 away. Did we mess this up somewhere? When we were here at F, no, yeah, we're good. E went to H. But you start to see how, and E went to H. So this guy is here as well. These are 2 distances away from A. To get to F, I have to go ABF. To get to C, I can go ADC. To get to H, I have to go AEH. And then finally, I would be a distance of 3 away. Step first versus breadth search. Questions? Okay, I'm going in my book. I'm going to page 899. Well, that's near the end of the book. Excuse me, what did I say? Page 899. Shooby-dooby-doo. Page 899. Uh-oh. Here's another name. Edgar Dijkstra. Hmm. He's known for the shortest path algorithm. Okay. So here's an algorithm. And we talked quite a bit about algorithms, writing something ahead of time. And oh boy, we got, yeah, add to the queue. Oh, a queue. Add to this boy, oh boy, oh boy. The shortest path. Okay. On page 900, all of a sudden, I start to see some class templates. If you go to D2L, crossing my fingers, if you go to D2L, let me go back to Zoom, let me share, let me go to D2L. You will see that I've given you code samples, chapter 16, HTM. And let me stop sharing and open that. Whoop, open that. Let me start sharing again. Boom, boom, boom. Not much share. Here we go. Oh, an adjacent yeah, digraph class template. That's nice that it's a template. Why? Because we don't know if we're working with integers or doubles or what type of thing. Yeah, look at that, baby. Glad I didn't ask you to write. Shortest paths of a network. Okay. Here's we're including digraph.h. So we're going to need that file as well. And I keep scrolling down to I get to a point where there should be a data file for the shortest path, and I'm not seeing it. Let me go back up. Where's the data file? Sorry, I know I hate watching when people scroll. Network file.data. Does anybody see a data file? I should have included that. Okay. I'm jumping over to the page 907. Page 907. Okay. You're going to have to make this text file called network file. So if you need to take a picture of it, if you don't have your book, yada, yada, yada. So how does this network file work? Well, the first city is Los Angeles. Los Angeles connects to three cities. Number three, which is Denver. Number four, which is Chicago. And number six, which is New York. City number two is San Francisco. It connects to three cities, one, three, and four. So I put the numbers in there so we got it. And on and on. Let's draw this digraph. I want you to draw this digraph. I'm going to figure out the US. Let's see. We have LA out here on the West Coast. We have San Fran. It's up above LA. We have Denver. We're going to stick here towards the middle of the country. Chicago is over here. Boston was in my data set. New York, Miami, and finally New Orleans. There were my cities. LA, San Fran, Denver, Chicago, Boston, New York, Miami, and New Orleans. LA goes to Denver, Chicago, and New York. LA flies to Denver. LA flies to Chicago. LA flies to New York. San Fran flies to LA. San Fran flies to Denver. Let's not run into each other. And San Fran, the last one is number 4, which is Chicago. Okay. This was 1. This was 2. 3 is Denver. Denver flies to 1, 2, and 3. Denver goes to 1. Denver goes to 2. Denver goes to itself. Must be a training facility. 4 is Chicago. Chicago goes to number 3, which is Denver. And Chicago goes to number 8, which is New Orleans. Boston goes to 4 and 6. Boston goes to Chicago. Boston goes to New York. New York goes to 4. New York goes to 7, which is Miami. And New York goes to 8, which is New Orleans. Miami goes to 8, New Orleans. Goes to 3, which is Denver. And it goes to 5, which is Boston. New Orleans goes to LA and to number 7, which is Miami. What do you think about that? Do you want to do a breadth search first? Let's just take a look at it. A breadth search right now. Pick a city.
LA.
LA. I'm okay with that. LA. Where does LA go? LA goes to Chicago. LA goes to Denver. Cool. Let's go to Chicago. Chicago goes to New Orleans and Denver. But we already have Denver, right? Denver goes, well, let's see. Denver goes to Denver. That's no help. Denver goes to San Francisco. Denver goes to LA. See, there's 1, 2, 3 exiting out. We're done with Denver. New Orleans. New Orleans goes to LA, which we have, and it goes to Miami. San Fran goes to Denver. We already have that. It goes to Chicago. We already have that. Miami goes to Denver. We already have. To New Orleans. We already have. And it goes to Boston. Boston goes to Chicago and New York. So from LA, I can get to any one of these cities. That first group was what? Chicago and Denver. And oh, we missed LA going to New York. My apologies. We missed that line. But we can actually get anywhere we want. And again, that was breadth. I went wide. LA went to Chicago, Denver, Chicago, Denver, and New York should have been inserted there. Okay. So I'm assuming that at least one person in each group is going to have. I'm only going to make two. I'm going to make two groups. Um, it'll be your normal groups. I'll open room one. I'll open room two. You know who's in that group. You can go there. Make up this data file. I want you to get the shortest path working. What's the shortest path from LA to New York? LA to New York. Well, shortest path is one. LA to Boston. LA to Boston, shortest path should be LA to New York to Miami to Boston. So it should be a shortest path of three. Oh, okay. Final is next Wednesday. You don't have to hear me lecture anymore. This definitely is the hardest comp sci course you took so far. Can I get some nods on that? Makes you think a lot, but we're told you're going to be prepared for Penn State or wherever you're transferring to. So I have breakout rooms. Thank you for the semester. It was a good semester. I'm going to let participants choose room. And those of you that go to room one, you can go there. Room two, go there. Get this shortest path algorithm working. It's kind of cool. And again, you're going to need that data file. You'll have to create it. And when you are done, we are done. What? The end. Okay, rooms are open.